Okay, fabulous. So a couple of the logistics that Kristen, it's up to you. We will be monitoring the chat, but if you want to answer questions during your presentation is fine. It's up to you, or we can leave it at the end of your presentation, and then you don't need to do anything extra with you may hear something on the ding, or if there's a participant is joining, but you don't need to do anything regarding that. And with this said, I'm welcoming everyone, and especially Kristen John, today to AAA Houston section SpaceGeekSpeak. She will be talking about the challenges of dealing with lunar dust, and she will talk about what lunar dust is, I expect. And with that, she's definitely did we just lose? Yeah, she is the subject matter expert in this area. She's leading lunar dust mitigation working group, among other accolades that she has achieved while working at NASA. And with this said, I did see that you were sharing, and now sharing is back to not sharing. So was there something intentional or not? Okay, I see the sharing. And
all right. And can you hear me okay?
yes. Mm-hmm.
Okay. Yeah, I lost connection for like 1 second there. So I don't know what that was. Hopefully that doesn't happen again. Cool. All right. Yeah, I'm happy to have discussion and questions throughout. So.
Okay.
Yeah, and I the way I'm sharing my screen, I cannot see the chat. So hold on. I'm gonna see if I can try to see the chat. Okay, I think I'll be able to see the chat too. So, and I see Ron Creel is online. That's awesome. He could give this talk too. So he can give the same talk. All right. Okay, so I'm here to talk about dust mitigation and some of the challenges with lunar dust as we head back to the moon. And so I threw this extra chart in there. I'm going to assume, because of the name of this group of folks, that you guys are aware of Artemis and aware that we're going back to the moon. And then I like to say too that 2024 is an exciting year up ahead, because we actually with Artemis, we as a oh, that's awesome picture right there, as a people are going back to the moon. And so with some of the commercial landers launching in January, Astrobotic and Intuitive Machines, and then there's a Japanese lander attempting as well, then hopefully we'll see some of those land on the moon. So it's a really exciting time, but I think I'm preaching to the choir here, since you guys are already space geeks like me. So yeah, as we head to the surface of the moon, right? And when I look at the moon, what I see is a challenge. We've got dust covering the moon. And most of what we know, a lot of what we know, is from Apollo. So we look back a lot to Apollo. And so we really appreciate everything we learned from Apollo, and especially learning from folks who are willing to share what they learned in their experiences. And so it's fun forum to be at, just seeing Ron. Ron's one of those folks who's gone above and beyond to help us capture some of those lessons. And so I really like this picture. This was something that NASA had put together for a challenge, a big ideas challenge, where we had solicited ideas from students at universities for how would you solve the dust mitigation challenge. It really is a fun challenge to solve, because there's lots of different ways that you can tackle it, but also it affects everything. And so even in this picture, you see the astronaut grabbing, the lunar dust, and you see the, unpressurized rover in the background there, and you can see a lander in the background. So, okay, so a little bit about lunar regolith. When we talk about bodies that don't have an atmosphere, so the moon, asteroids, that's where I started my career at NASA, was actually studying small bodies or asteroids, and other bodies in the solar system. If they don't have an atmosphere, what we have is basically regolith, which is this fragmental layer covering the surface. And so it's technically independent of rock size and composition. And so when you think about lunar regolith, when you think about like the surface, it's really angular, it's really abrasive, it's irregular in shape. So you can see a couple of pictures there. And because there's no atmosphere, it was created by the bombardment of the solid lunar crust by meteoroids, solar UV flux, solar wind, radiation over billions of years. And so during this process, we have this formation of what we call agglutinants. And so it's basically fused particles of impact class because of the bombardment. And so that's why it's much more like, when I talk about it to folks, it's much more like shards of glass than it is like household dust. So, and to clarify, we also have regolith on bodies with atmospheres, right? So you have, you have this on other bodies as well, but the way that it was formed is different on airless bodies. And so you can see some pictures there of the structure, how deep the regolith is. It can vary by location. Eventually you'll get down to more of like the solid bedrock, but this layer of regolith, this fluffy, loose stuff that you hear in a lot of the astronaut quotes, the stuff that we care about when we talk about dust mitigation, that's what we're here to talk about today. This picture here, I really like the close-up of the boot print in Apollo 12. Even the idea that they took pictures of the boot print. There were actually studies done with these images to study the cohesiveness of the regolith, because before we went there, we didn't know anything. Okay, so regolith, dust, we use that term interchangeably. So if you talk to a geologist, planetary scientist, someone else, you're going to get, into a debate about the definition of dust. But in the literature, right, we use the phrase dust mitigation. So that's just what we call it. But if the geologic definition oftentimes is referred to less than 20 microns, for the purpose of what we do, dust mitigation, we talk about all lunar particulate that needs to be mitigated. And if folks aren't familiar with scale, this graphic here helps. So a human hair, the diameter of your human hair is 100 microns. And so here's a couple other things. Smoke particles about 1 micron, pollen is 30 microns, bacteria is less than 1 micron. And when we talk about the average particle size of lunar dust, that's about 72 microns, so about the width of a human hair. If you get less than 50 microns, that's less than the visible eye can see. And then you can see just a couple more facts there if people are interested. So one thing I will say, we do say for dust mitigation, it's all lunar particulate that needs to be mitigated within reason, right? Once you get above a certain size, I'd say sometimes we say that's above 100 microns, sometimes it's above 500 microns. We joke that that's a boulder in our world, right? And so just, with various effects of the forces on the moon, that's not the stuff that we are as worried about, but it really is system dependent. And so from a human health perspective, for instance, they're really concerned about the really small stuff. They don't even care about 72 microns. They don't even necessarily care about 20 microns. It's the really small stuff. And I'm not an expert in that. I'm not going to talk about that for too long. We have folks that do that. But, if you were, worried about like the mechanisms in a component, it might be 20 microns. It might be 70, it might be 150. And oftentimes you have to do testing to figure out what that is. Or maybe it's a combination of those things. Just a couple pictures there to show pictures of lunar dust and what it looks like. And so again, we say that it's not like your average household dust. So in case you're not sure what household dust looks like under a microscope, that's what it looks like. And so there's some really great pictures from Southampton University taken with a scanning electron microscope. And if you go to this website, if you just Google this, it's really cool. You can see images of like all of the things you've ever thought of. They've got really cool pictures and you can see, oh, what does this look like up close? And so if you look at, household dust and some of the other things that you might find in your house that you would consider household dust, the normal things, right? Skin particles and fingernails and whatnot. It's going to look kind of like that. Lunar dust, right, looks nothing like that. Okay, so a lot of words on this chart, but I think this is important when we talk about the lunar dust. Why is it such a problem? And it's partly where we're going, and it's partly where we are, because we're trying to study the problem here, but we're going there. And so Ron actually talks about this a lot. So first of all, it's electrostatic and ferromagnetic in environment with no natural grounding. So it sticks to anything carrying a charge. So we see that a lot with some of the history, the way it behaved. So it's fine grained, like I talked about. So much of it you can't see with the human eye. So in, space flight, we talk a lot about visibly clean, on the space station, visibly clean, or getting hardware ready to send up to space. Well, we can't use that terminology anymore. It's jagged, angular, like we've said. And so it scratches everything from, a visor, like on the first slide that I had, to suit fabrics to human lungs. And then also, if you look at a map of the moon and where we've been, we've only been to a couple of places, right? It's like we've been to, like Clear Lake and the Woodlands, right? And we haven't been up to, to Dallas or down to Corpus Christi. So we only know about the composition of the dust in the places we've been. And so Artemis is going to look very different. It's unpredictable. And so the behavior of lunar dust in space is governed by different forces than on Earth. That's a big one. And then it's difficult to analyze because it's very hard to replicate our behavior. One, because of gravity. We all wish we had that anti-gravity chamber that everybody asks about. And then zero, the atmosphere. And then that also makes model validation difficult. And then also say that, thermal and vacuum and all of that together, it's just not as simple to replicate as well as it's done on the moon. So if we could just go to the moon to do all of our testing, that would be fantastic. This was taken from a challenge, one of the student challenges that we've done. And I thought this was just a fun way to kind of summarize lunar dust, which is it's ubiquitous, abrasive, and electrically charged. Okay, and then insight from Apollo. So we take a lot of what we know and the challenges that we're going to face from Apollo. And so if folks are interested in learning more, if you read anything by Jim Geyer, he's put some great resources out there during the constellation days. In particular, this one paper in particular, the effects of lunar dust on EVA systems during the Apollo missions, is great. But in particular, he captured some of the things that we knew about as soon as we got to the surface. So false instrument readings, human health toxicology, clogging of joints and mechanisms, vision obscuration, abrasion of surfaces, failures of seals, and thermal control. Pretty much anything that touches the surface or it's, exposed to the surface and comes back inside will have some sort of impact from lunar dust. Even Gateway, we work very closely with Gateway on their lunar dust challenges. So we have what I read this in an article and now I love this, the Dusty Dozen. We like to refer to quotes from the Dusty Dozen because there's a lot in there, right? And we don't have a lot of quantitative data. So there's some really great quotes. I could literally talk for hours just reading you amazing quotes. And so I just picked a couple here that are great. And this is good for business, I think. Dust is the #1 concern in returning to the moon. So John Young said that. Gene Cernan, this one we use a lot. I think dust is probably one of the greatest inhibitors to a nominal operation on the moon. There's a really great quote that Gene talks about that talks about the adherence of the dust to everything. And then this one Gene Cernan quote I think is my favorite. I ain't going to do much more dusting after I leave here ever. So kind of fun. This is just like a fun graphic that we had put together that shows, that dust poses challenges for everything, right? Solar panels, electrical connectors, gears, mechanisms, optical systems, mobility even, or, anything with a, crevice, human health. You can see the poor astronaut in their eye, in their nose, right? It definitely caused irritation during Apollo for some of the astronauts. And so even like the impact, the plume surface interaction effects during landing. Okay, and then this is just kind of a word cloud of other things. And so again, we could get people in here to talk about all of these things. Ron Creel could talk about even the mobility aspects of some of this stuff. And so all of these are considerations that we have. And you'll notice even some of these are things we deal with on the surface of the moon, and some of these are once we come inside, even like aerosolizing the dust. What do we do once we're back inside? So the problem is kind of far and wide. Okay, so when we talk about some of the history and some of the failures, One of the things that I like to relate it back to, especially for folks that follow space examples, right, is when large systems fail, it usually happens when there's multiple things failing together, things that maybe you couldn't anticipate. And so we've seen this. We've all, those of us who work at NASA, right, we all study Columbia and Challenger. That's a big part of our jobs, is to make sure we understand that history. And even if you look at 3 Mile Island, it wasn't one thing that went wrong, it was multiple things. And so this is, you know, I believe, right, a big part of the dust challenge is it's not just dust that's bad, it's what the dust does to your other systems. And so it's kind of this confluence of environmental factors. And so we look forward to Artemis 3, Artemis 4, Artemis 5, but when you really look forward to sustainability, to, you know, presence on the moon, and you think about some of these, you know, rovers and whatnot, and why we will have challenges with all of the Artemis missions. When we think about sustainability, you know, we haven't done this before. And so when we went to Apollo, we went pretty quickly, right? And what we're trying to do now, right, we've seen with the Indians and whatnot, is we're trying to survive the night. And we haven't done this before. We haven't. Some folks have. But the idea there is, you know, thermal considerations, power considerations, optical considerations, communications. And so dust is going to play a factor in all of those things. We know this, and we actually do have evidence of all of that, you know, from Apollo and from other missions as well. So, you know, for example, on thermal, dust will coat radiators, and that will increase the temperature, right? So then your radiator could become an insulator. That's not a good thing. For power, dust accumulation on solar panels can lead to reduction in available power. For communication equipment can be covered in dust. Even, you know, for all of these things, right? Electrical connectors, if you're trying to connect things in the dust, optical, that's, you know, something we saw immediately with Apollo. You know, whether it's again, anything from a visor to camera to optics, and then even down to the optical properties of other equipment, you know, that might be affected by, you know, dust on something, or dust then affecting, say, the thermal properties that then affect the, you know, the reflectance or the absorptance or something like that. So it's very, you know, cross-disciplinary problem. We work very closely with power folks, thermal folks, and so on. Okay, another one bites the dust. So we could talk about this for hours, just all the challenges, all the lessons learned from the surface. Jacqueline Black, who's another dust buster, as we call them, on our team, gives a really good presentation on Apollo lessons learned. Ron has some really great information there. So that could be a whole nother talk if folks are really interested in this. But even Apollo astronauts couldn't avoid getting dust deployed on the ALSEP experiments. That's, you know, one example. One that I really like, and there's like a whole story behind this that I like to share. But the Lunar 2 rover, a Soviet rover. So there was a Lunar 1. It lasted for like 10 months, I think. And then Lunar 2 only lasted 4 months. And it had to do with dust getting on the solar panel. So you can see the picture there when it went into a crater, and then the solar panel closed, and then dust got on the radiator. And then a couple of days later, it stopped working. So a lot of times we have to make inferences, right? And so I like to just blame the dust. But you can make inferences that it's very likely that the dust led to the demise of some of these. No doubt dust was a problem on spacesuits. There was an issue with a connector on the glove that, had they needed to go out on one more EVA, they might not have been able to. And communications, TV, cameras, and equipment, that James Geyer paper goes into all the details. And then even just the dust accumulation on the radiators for the LRV for Apollo 16, but really a lot of the Apollo missions was a serious concern. And again, that we weren't even there for that long. So when we talk about the lifespan of some of these other rovers that are going there, you know, it's an even bigger concern. More lessons from Apollo. The Apollo astronauts encountered marked degradation performance in heat rejection systems for the LRV, the Lunar Roving Vehicle, science packages, other components. And then if you look at some of the thermal control issues, an insulating layer of dust on radiator surfaces could not be removed and caused serious thermal control problems. So, you know, this is something that we're studying, that universities are studying. We're trying to get smarter on this problem, and we're going to get smarter as we go to the surface, for sure. Okay, lunar dust on power and thermal systems. So when you think about what is the function of different thermal systems and power systems, you can see some of those laid out there. And just a picture of Mars. Mars is an example. And so kind of asking facetiously, what could go wrong? And so here's examples of what could go wrong. Internal clogging and scratching of power connectors, heat rejection and radiators. You can have performance degradation, lower efficiency, system overheat. If you have reflective surfaces, those will be compromised by excessive dust. Mirrors can be obscured. Power generation and solar arrays, you can have solar thermal conversion effects such as heat absorption, reduced power output. For PV arrays, cells, and sensors, you can have reduced power output, lower efficiency. And so we have, again, we don't have quantitative data on a lot of this, but we can make inferences from Apollo that these were serious issues. We do have data from Mars that does show that just a little bit of dust causes pretty significant performance loss. And then we are doing data on the ground as best we can, replicating the environment to show that, yeah, dust is bad. So hopefully I've done my job to scare you all. So did radiators degrade during Apollo? Yes, I'll just leave it at that. So the data's here. This isn't one of those Jim Geyer papers that shows, again, making inferences about, that we believe from the dust that, temperatures were higher than expected, that the batteries, got hotter than expected, and so on. And again, just emphasizing that these were much, much shorter missions than what we're expecting for some of our future rovers. Okay, so what are we going to do about this problem? First of all, say it's an all hands on deck kind of problem. Anyone who is a hardware owner or program person at NASA or a university student thinking about building something to go to the surface should be thinking about the lunar dust. That's my goal, is that you look up at the moon and you think, dust, what am I going to do about it? So if it was up to me, right, everyone would have a dust mitigation strategy, or just at least be aware of the concept of dust mitigation. And so at a very high level, this is what we want people to do. First, understand the natural environment. Be aware of the moon, right? This isn't low Earth orbit anymore. We are going to an environment that is unlike where we've been. And so understanding the natural environment as it is, and then understanding the induced environment. As you get there, what are you going to do? Are you landing a giant rocket that's going to blow the dust everywhere? And where's that dust going to go? Or are you, a little experiment that's sitting here and then another lander is going to come and blow dust on you? That's good to know. So understanding the induced environment. Are you just an astronaut walking around, but you're going to induce dust, move dust around, all of those things? That's really important. A lot of that, there's a lot of factors that go into understanding all of that, and we try to help folks do that. Understanding tolerance to dust. What is your system? Are you in charge of the spacesuit? Okay, you need to know, can your spacesuit, outer material, outer garment, outer fabric, whatever it is, tolerate dust? Are you in charge of the solar panel or the radiator, or are you in charge of the crew cabin of Gateway, and dust might come back inside? Dust will come back inside. What are you going to do about it? So understanding tolerance to dust, and then if you have the ability to develop environmental requirements for limiting dust, or keeping dust out, or once dust gets in, tolerating dust, for instance. And then selecting dust mitigation solutions, right? And my role is really dust mitigation technology development, but you don't jump right to what is the solution. You really need to understand the problem. And then we kind of have a loop here for testing. Ideally, you would do testing in order to understand tolerance to dust. I do believe as we do more and more, as more and more hardware goes to the surface, we'll have a better understanding of tolerance to dust of systems that I hope we can share. And folks will share, hey, look what we learned about the effects of dust on radiators. And we, NASA, are for sure sharing what we learn as much as we can with everybody. But then as others, learn through forums like LSIC, the Lunar Surface Innovation Consortium, and others, we're trying to put that information out there. But more testing is for sure necessary for all hardware owners if you're going to the lunar surface or expecting to be exposed to dust, to understand the tolerance of your system, and then to understand the effectiveness of your solutions. Okay, so what do we do about it? It's pretty common sense as far as how you manage the dust. One, tolerate dust exposure. If you can handle dust in your system, great, don't even worry about it. Then detect and monitor the dust, so you know how much dust is coming into your system or onto your system or into your into the gateway or into the human landing crew compartment or whatever. Control the entry of dust into your system. So if you know I can only have X amount of dust in my mechanism or in my crew compartment, you need to figure out how to control entry into your system. And then the last step is removing the dust, right? Try not to get the dust in there. The only way we can really keep the dust out is not going to the moon, and none of us want to do that. So then we get to solutions. And so there are architectural solutions, operational solutions, passive technologies, and active technologies. That's how we group them. And so a couple examples: architecture and operational. A lot of times you don't get a say on that. That's sort of defined by the architecture. But it might be something like, does your does your lander or your habitat or whatever have a suit port, or an airlock, or a multiple volumes, for instance, right? That you can, leave some of the dust behind, or can you have some sort of mudroom, or, a porch even, we talk about like porches, or some place where you leave as much dust as you can outside. And then when we talk about, and there's other ways that you can kind of think about architecture and operational solutions. It could be something as simple as, it's not simple, folks won't like me for calling that simple, but it could be something like, if a lander is going to land here and blow dust X amount of distance, which even determining how far that distance is not as simple as folks think, right? But if once you figure that out, you can say, okay, I want to take my rover, if you have mobility, and drive my rover this far away so that they don't get dust on me, right? So for more static payloads and experiments, that might be a little bit harder. But do you have the ability to say, okay, please don't let the lander land this close to my habitat because I don't want dust on it, for instance. Okay, active technologies and passive technologies, we define, that definition. We use the FEMA definition. So active we define as, do you require power, and passive, no power, basically. So depending on how you define power, right? Do you need a human in the loop to use your system? And if that's the case, then a brush would be powered. So it kind of goes back and forth. But passive, I think of as brushes, tapes, adhesive, wipes, even like coveralls, aprons, even like, a soft wall that you might put up inside a crew cabin, or even like a tarp you might put outside. Even filtration kind of goes back and forth between active and passive, but filtration, or some sort of way that you remove the dust inside. Active technologies, we look at things like electrostatics. We look at things like, compressed air, ionization, vacuums. The electrodynamic dust shield is a big one. That's a specific solution. So I'll talk quickly about the solutions, but I'm not going to get into the solutions a lot here today. We do group them in. We do kind of talk about dust mitigation technology in 4 what we call swim lanes. Dust tolerant components, which includes mechanisms, seals, bearings, joints, covers, for instance, like how are you going to protect your little component, whatever your component is. Passive solutions. So really we think of coatings, or really like modifying the surface, materials, filtration. You can really think of passive as something you can do to your hardware before you send it to space. That's kind of how I like to think of it. Active is, you need to like do something. Once you're there, like you need to apply power. You need to, do something to it. So electrostatics, compressed air, vacuums, and then dust measurements. That's really us getting smarter. A lot of us in the community, not just NASA, we have a big community, kind of all in this together. We want to learn more because there's a lot we don't know. And so a big push for us for the next couple of years is to learn as much as we can from the missions to the moon. And so, we're trying to collect as much data as possible to put those back into models, so more sensors, more ground experiments, more characterization. So we do leverage common kind of terrestrial solutions. I've talked about some of these, but things like soil stabilization, they use this in deserts and whatnot. And so some of these we've talked about. So I'll go through that. Even gels and putties, stuff like that. Filters is obviously a huge industry terrestrially. We do use the small business opportunities here at NASA to develop technologies as well. Desserts, and detailing your car. So we try to learn from other industries: mining, cosmetics, food and baking, pharmaceuticals, contamination control, clean rooms, household dust mitigation, living and working in deserts, exterior car cleaning. So all things that we try to leverage and learn from as we come up with solutions. Given that, the environment of the moon is very different, right? So you do have to introduce, take into account the electrostatics and other things that we don't necessarily have to worry about here. So, all right, and I'm almost done. I will, for sake of time, I'm going to skip over some of these, but these are just a little more details on some of the solutions using compressed gas, some of the pros and cons of some of these things. Electrostatic precipitation. Yeah, this is into the nitty gritty, which some of you might like, but the electrodynamic dust shields, if folks are interested, I don't have a video here, but it's worth looking at this. It actually takes advantage of the charge of the particles and literally like changes the charge of the particles to walk the particles off the surface. So really interesting technology that's kind of widely used as a potential solution for dust mitigation. Testing with dust. And so this is something that we actually look to give to as guidance for folks that are looking to test. And so kind of steps that they use, a big part of testing. So we have a standard that folks use that's publicly available, 100-page document on how to do dust testing. But also simulants is, unfortunately you can't go get, Apollo samples to test with. And so we have simulants that folks use to test with. And then where do you do your testing is a big question too. So identifying your facilities. So simulants, that's probably the most common question I get. What simulant do I use? And so there's a whole committee at NASA, mostly geologists, but other folks too that really understand kind of like the geotechnical properties, depending on what testing you're doing, right? If you care about abrasion or if you care about, seals, or depending on what you care about, there's different properties in a simulant that you want to pick. Also, how much quantity do you need? Are you doing a giant test in a giant test bed versus like, small quantity? So these were just a couple facilities at Johnson Space Center that we have for folks that, I don't know if folks are doing testing, so I'll probably skip over this. Plume surface interactions, that's, I think there's some folks that are engaged in this community that can talk about this a lot better than I can. But this is, as the rocket lands, it creates this, plume of dust that goes everywhere. And so that's what causes a huge amount of the dust challenge that we do see and we do have. Not to say it's the only challenge, right? But that is a big one for us. I'm going to skip over this for time's sake, but this is just to say that, we have, during Apollo 12, we actually took samples to actually quantify some of this, which is really neat. And then during Mars missions, even something like a lens cover to protect the lens didn't work. So plume surface interactions are intense. So that's the camera lens that didn't quite do its job. This is just for those that don't know, the Lunar Surface Innovation Consortium is a wonderful forum to kind of get engaged. And it's all about kind of the future of the lunar surface, about kind of like sustainability. And as we go back, to the surface, it's very focused on, technology development, but also, what are we going to do? We talk about things like interoperability, we talk about dust mitigation, power, infrastructure, that sort of thing. So if folks aren't engaged in that, anyone can join. Please consider that. So a couple resources here, if folks are interested in reading more about dust mitigation. There's a new document that was put out. It's pretty easy read about kind of like best practices. Yeah, this one here, Lunar Dust Mitigation, a Guide and Reference. So there's that. And then I just wanted to end, and I think I know I talked longer than Svetlana told me to talk, so I apologize. But I want to end with a quote that I think is important for all of us. And says we're headed back to the moon, hopefully landing on the moon in January or February, just a month or two from now. I think it's important to reflect on this quote that maybe you've seen. You've probably seen it, but maybe you haven't seen all of it, which is that as Neil Armstrong got to the moon and got off the ladder, what was it that he was talking about? So here he is, right at the foot of the ladder. Foot pads are only depressed in the surface about 1 or 2 inches, although the surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. Down there, it's very fine. I'm going to step off the LM now. And he says what we all know he says, right? One step, a small step for man, one giant leap for mankind. Then he gets right back to talking about the dust. The surface is fine and powdery. I can pick it up loosely with my toe. It does adhere in fine layers like powdered charcoal to the sole and sides of my boots. And so just wanted to kind of share that the moon is covered with dust. We know that. And so I hope that, as folks kind of look up at the moon and think about this challenge, that you'll remember the dust problem. So I will leave it at that and answer any questions that folks have. Thank you.
That was great. It's so nice to get all this information and share it with everybody.
So thank you for having me. I appreciate it. And I do see the question now from Esther there. Can dust mitigation affect the atmosphere of a planet, or does it only apply to lunar objects? I'm not sure if I'm totally understanding the question there. Like, does it have an effect on like the atmosphere, so on the moon, there's not really an atmosphere. So the dust literally just settles, right? And so as the dust, like even with plume surface interactions, as the dust goes up, or as a rover drives, right, as soon as like the rover stops, the dust will just settle. So I'm not sure if I'm answering that question there.
Kind of the way I read it is we often think of planets as having atmospheres, but moons not having atmospheres. I mean, maybe an overgeneralization, but I mean, dust on a body that has an atmosphere versus dust on a body that's like the moon with no atmosphere.
Sure.
But yeah, in general, I guess to Esther more, the answer is that dust mitigation affects everything, not necessarily atmosphere of the planet, but what we are mitigating is the impact to things that we want to work, and not just things, but humans as well, including in that loop of everything that needs to work, needs to survive, and that needs to maintain its capabilities. And that is the idea and the whole purpose and the goal of dust mitigation, of all the dust mitigation techniques that we are developing and in future will be developing.
That's exactly right.
Yeah.
And there's a whole nother area called planetary protection, which is basically about protecting the planet. So that's not my area at all, right? For me, it's exactly what Svetlana said. It's protecting the hardware from the planet, right? To me, the planet is bad. The moon is bad. It's not really, I love the moon, but the dust is bad. What's it going to do to my hardware? But then there's a whole nother area of people, right? Where they're like, you know, evil hardware people, you're going to bring your bad, dirty, contaminated hardware to the planet and get it dirty. And I think this is not my expertise at all, but that's a bigger concern for like Mars and other planets than it is, say, for the moon. Again, not my expertise.
So, and you mentioned some sources there. I'll have to dig into those because I've been wondering about whether cathodic protection techniques that are used on the Earth, where you have a sacrificial anode, for a buried metal pipe or wires or something like that, would allow you to kind of reject electrostatically some of the dust on equipment and just kind of keep it from getting on in the first place. Because a lot of techniques, of course, are once something's already got some dust on it. But if you can keep it off in the first place, you might have helped your equipment out.
Absolutely. Yeah. And yes, please. And any ideas that folks have, feel free to shoot me an email. I love forums like this because one of the things with dust is that it's very much like, like we showed, we leverage kind of what's been done terrestrially. What are the other ways that we can, mitigate this challenge? Because are there new ways, new ideas we haven't thought about it? Yes, but if you could keep the dust from ever getting on the surface, one of the things they talk about is even like, we talk about coatings a lot, but even surface modification. If you can modify the surface so that the dust, the particles can never stick to it, that's a big thing. And so, if there's a connection that anyone has made, like, oh, have you tried this? Have you tried that? Yeah, let us know, because, we do have we do the, hackathons, and we do the, a lot of student challenges, but we haven't made all the connections, that's for sure. So I'd love to hear them. So.
And most likely thinking outside of the box will bring the best or the most practical solution for whatever problem. And I agree with you, Kristen. There's most likely no one size fits all, depending
Yes.
on what surface, depending on
Yep.
the goals and the purpose of that equipment or humans, that
Yep.
there would be a different type of solution.
Yeah, absolutely.
So there's a few comments, questions
Oh, I didn't
been
scroll down.
posted. One I see that after Esther had posted that Tom Bryan made a comment about the SpaceX HLS elevator that could be at risk of jamming from dust. Most it potentially, depending on what uses for the transfer of the movement. And some of the smaller the gears most could potentially jam.
Sure. Yeah, and I'll keep that one generic. I would say yes. Any mechanism that's going to be exposed to the surface, absolutely has the potential, I think, to be at risk from jamming and gunking up, right? And so I think that there's certainly work that we can leverage here, right? We do look at some of the you know challenges that we face terrestrially for the way mechanisms work and grind through tough environments. And so but I think that when you look at the moon and the fact that we are operating completely outside, for sure, absolutely a challenge that having a good dust mitigation strategy will can be overcome.
And Mike asked something I hadn't thought about. Is there any difference between dust in lunar day and lunar night?
Yes, there is. So I'm not an expert on the electrostatics, but the charge changes, and I'm going to get it wrong, but yeah, the charge can change, to my understanding, right? And sometimes we'll talk to scientists that have different opinions on this, but yes, the charge changes depending on the night side versus the day side.
Okay.
So yes, so that's, again, the environment's very complicated. So even when you talk about where you land and where maybe you have a payload, say on a lander, where if it's sun facing or not sun facing, or if it's nighttime or daytime, lunar night, whatever, all of those factors are important.
Thank
and
you.
there's even theories about the charges and the behavior of some of the dust in some of the environments that we're going, like in the South Pole and whatnot. So I will say, one of the things that we capture is a lot of the unknowns about the dust, a lot that we don't know. So we are making a lot of even the standard that we have for testing, a lot of these things we have to make kind of some assumptions, kind of worst case about some of these things, because we don't know all the answers. So.
Okay, Kai asked about if there's a way to tell how compact the dust is on the surface to use in the prediction for lander dust interactions.
Yes. So they have done it from imagery. They tried to do it from imagery from Apollo. And then I know when you're on the surface, there's tools to do that. So I don't know how else they do that. Some geotechnical person type, geologist will have a better answer to that than I do. I do know that, that whole the lander dust interactions is a huge area of research. It's big in NASA, it's big in academia. There's, models out there. There are a lot of unknowns. And so there's some really cool videos. There's one that's been going around recently of like the kind of a new, newly generated graphic of the Apollo landing. But the Apollo landings are very different than what we're going to see with some of these other landers, right? The scale is just totally different, I'll just say. So, but also, we're going to learn, I believe that we're going to learn a lot from these landers that we're going to see in this next year, which is really exciting. So
right, with Intuitive Machines and some other companies that are planning, right?
Yeah,
Planning
exactly.
to
So
have a landers next year.
Yeah.
And I think you mentioned that the data so far that we have from lunar surface is very sparse and very, in many cases, very old. And
Sure.
whatever we are going to get is going to be because of the the sensing techniques have changed since the last data has been collected on the lunar surface, and the way that we can interact with that and absorb that or pipe it back to the Earth changed too. So with the digital technologies that we have developed since our first lunar exploration, we will be able to collect way more data and most likely be able to work with that data in a much better way and in order to support our further exploration of the moon.
Absolutely. Yep. Yep. And to add to Kai's question too, because I'm not totally sure, and I'm going to ask someone later to make sure I know, so I can answer this question better. Also, we do have a lot of orbital assets, and so I'm not totally sure with the instrumentation that we have remotely how they can detect, things like, compaction. I don't know if that's even possible, but I feel like when I hear about some of these ground penetrating radar, other things, I don't know how well those things work. But there certainly are tools, and we have information on that. But again, there's error bars, I think, on all of these things, to my understanding. So.
Okay, I think Esther had made a question as a comment too, that it's reinforcing the message that you have in your presentation about the effects to health of the human. Yes. And also their environments. And yes, sure. It's basically very negatively potential effect. But if you want to expand on that.
Sure. Yeah. So we at NASA, one of the things that happened after kind of started during Constellation, but continued afterwards, which is fantastic, was a study with geologists and toxicologists to kind of quantify as best we could, right, the human health effects from lunar dust. And so there's a report called LADTAG. You can read about it, LADTAG. And they, they used rats. We didn't use human test subjects, right? But and so kind of taking actual Apollo samples, right? I did say we can't get Apollo samples to do dust mitigation, but they were an exception, right? And they did this like 3-year study, and so we do actually have requirements on how much lunar dust a human is like the safe limit for human limits. And so the nice thing I will say is when we talk about lunar dust mitigation for crew compartments, whether that's for HLS for human landers or for habitats or pressurized rovers, we do have that requirement figured out. This is public information. You can go look it up. But this is so we do have a requirement for that. Not to say that we have everything all sorted out. We don't, right? But there were only 12 subjects that went to the surface. There certainly were effects, but it wasn't like, again, this is not my expertise. We have, health and medical technical authority people that can talk about this much better than I can. But there were effects from Apollo, but it was more like irritation effects, right? Irritation to the eye, irritation to the nose. But when you look at the small particulate that you inhale in the lungs, that's the bad stuff. That's the scary stuff. So when you look at the requirements that we have that are very stringent, it's to protect the lungs, really, right? To make sure it doesn't get in there and really, you don't inhale too much. And so how we solve that problem, right? There are certainly ways to solve that, right? And so this is something we have, filtration. We have even things like masks, right? I'm sure, we all familiar with that concept now, right? And so, but yes, it certainly is a health hazard. I think there's more to learn about that, but for now, at least I would say that's like the one area in dust mitigation where we actually have like a really good requirement, right? If you were to ask me like, what's the requirement for how much dust I can have on my radiator? There's not one person who can give you a good answer for that. We do not have that information. How much dust can I have, in my mechanism? There's not one person who could give you an answer for that. Don't trust them if they tell you, right? But for human health, we do actually have a requirement that's been established, and I'd say it's pretty stringent, right? You have to get your crew compartment pretty scrubbed for safety and health reasons for the astronaut to keep them safe. So.
Well, looking at that photo you had of Gene Cernan, I mean, he had dust all over him,
right?
His clothing and everything, and yeah, exactly. I mean, it's like you can't imagine ever getting that environment clean, really. And so, yeah, any dust, of course, that's on surfaces you're not breathing, but a surface that gets brushed with a hand or something could reintroduce it, because it gets low gravity, and then it's right there to be able to breathe it in. And I can't imagine there's any way you can, vacuum dust out of somebody's lungs or something, because
Exactly. Yeah.
if it's stuck in there, it's stuck in there,
Once
right?
it's in there, it's in there, right? And so, that's exactly right. Yep. So it's if you really read some of those Apollo quotes, it was. I mean, they were dirty, and they would spend a lot of time cleaning, and they could not get it off of themselves. And that was quick, right? They were not there long, and so we really have to be considerate when we look at like, not even just the shorter stay missions, but the longer stay missions. So, but they've already, they've even taken those into account. The the amount of exposure. So these are permissible exposure limits, and so again, it's a little bit out of my wheelhouse here, but it's about how much exposure you can have over a certain period of time, right? And so there's going to be a peak, right? When you come back from an EVA and you're taking off your suit, right? Like there will be peaks of exposure, kind of like radiation, right? And so it's about like how much you can be exposed to in your lifetime. And so there will be peaks, and so it has to average out to like, okay, you need to stay below this. So that is really hard to do if you don't have a monitor, right? And so that's a big thing that we push for, is we want to monitor the amount of dust. We have no data. We don't know how much dust came back inside. We look at that picture of Gene Cernan and we're like, I wonder how much dust that is, right? We've done things where we'll put dust on like a spacesuit and like different amounts of dust, and we're like, like based on like how much dust do you think was coming? We have no clue how much dust came back inside from Apollo. We have to guess at it, which is really not fun when we talk to requirements people and they're like, we want to quantify this amount of dust. How much dust is coming back in? And we're like, well, yeah, we're looking at a picture from 50 years ago and guessing. So,
well, and that's why pictures, or even more the data, the hard collected data that will be coming from from those lenders, most likely will be invaluable, and and not just the accumulation, but what I'm curious that most likely will be also helpful and needed is that the plume that generates with the landing, right? That all the dust that will become airborne, no, whatever it is, lunar borne, right? Because there's no air in the same way, but whatever becomes just dislodged, and how long will it take for it to settle? When is it safe for whatever it is, either to open all the surfaces to start collecting energy from the sun, and how long can it be exposed? I mean, there's so many different questions that from the systems perspective will have to be answered.
Yep, absolutely. Yep. And inside the crew cabin, it's the smaller the particle, the longer it takes to settle, right? And so we do actually have good data on that. And then it's affected by the pressure, right? And I think the pressures are different that we're expecting, I think, than what we saw in Apollo, but inside the crew cabin. And so we do have data on like the settling times, but it takes a while. And so, it really is an integrated challenge. You have to take into account like your filtration system, and when you're done, kind of getting out of the suit. So, and then there was a question in the chat about how the human body gets rid of lunar dust in the lungs. And it's the same way we get rid of all particulate. Certain amount, right? You can cough up a certain amount, just won't get into your lungs, and a certain amount you'll cough up or comes up through like mucus or other stuff. And I know all this from the toxicologist, just like what I've heard, not my expertise, right? But there is a certain amount, the really small stuff, and I forget what the number is, if it's under 2 microns or under 0.0 something, really small amount, that once it's in there, it's not coming out. And so and this is the problem. This is one of the challenges with lunar dust. It's the really small stuff that's really bad for you. It's also the really small stuff that's harder to capture. You also can't see it, right? And so you might be like, oh, it's clean in here. Well, is it, right? And that's why we need monitoring, and that's why we need good filtration systems. And so, again, these aren't challenges we don't have here, right? Filtration is a huge thing. HEPA filtration, this is something we use regularly here to keep air clean. And so we leverage those. But it's the smaller stuff is really problematic for human health reasons. The smaller stuff's also hard to capture, hard to quantify, hard to measure, even hard to, we don't even know how small the small stuff is. When we brought the samples back from Apollo, getting the samples out of the sample containers, the really small stuff, you couldn't even get out of the sample containers because of the way it adheres. Even the tools to like use that stuff, right? So like some certain stuff, once it gets in your lungs, it never comes out. So, and this is a challenge we know from other, this happens in other industries, mining and other things too. So, and I see Ellen has a question.
Trying to get to the mute button. And yeah, you ended that with the right thought that I had. You mentioned mining. There are other industries too. For a little while, I worked for the US Mint, and they would strike metal coins with a press, and it produced a significant amount of very fine metal dust.
Wow.
So it's
Cool.
not the same. It's because it's metal dust, but they had problems with that for years. And obviously, as time went on, they came up with better and better mitigation strategies.
Sure.
But you might want to also look at mining and manufacturing and see what other, it's not the same as regular, but what did they do with these very small particles to kind of mitigate that?
I'm adding that to my list. That has never come up. Other manufacturing things, like was someone talking about recently, other manufacturing processes do that, but I never heard of the US Mint example. So cool. What mint did you work at, if you're allowed to say?
I worked at the Philadelphia Mint, and it was really good.
Franklin Mint? Is that the Franklin Mint?
At the Franklin Mint, and it was wonderful.
How cool.
Oh, check it out.
Yeah.
Yeah, and
I lived in Philly as a kid, so I actually remember going to the Franklin Mint as a kid. That's really cool. Thank you, Ellen, for that. I really appreciate that. I'm adding that to my list. That's a connection that's never been made for me before.
You have to give it a try, because when I would have to go in there, I go up there, I would have to put on all this gear to go in there, and everything was just covered in metal dust. So, and I grew up in Philadelphia, so I know. Visiting all those great places in Philadelphia is so fun. So check it out.
I will. Thank you. Yeah, so I gave a talk at Pumps and Pipes. I'm assuming we're all Houstonians here. If folks aren't aware of Pumps and Pipes, gotta go. It's so cool. It's aerospace, medical, and
oil
energy. Yeah, all come together once a year, and they didn't have it, I think, a couple years during COVID, but they just had it a couple weeks ago. Yeah, it was really cool, and especially if folks really are like proud Houstonians. It's just like very innovative, and it feels like, anyway, yeah, I got a couple really great connections there where one person was like, oh, my friend has a such and such company and manufacturing company, and he has a dust mitigation plan. I'm going to connect you to him. And I'm like, oh my gosh, that's amazing. So yep, coal mining is for sure an industry that we've tapped into, and then and we've done kind of coal mining, and even the desert storm. I don't know why I said desert storm. Desert industry, because one thing, right, is the amount of money, I'll say, right, that's gone into dealing with. That's why I said desert storm. I think, right, is the fact that that a lot of resources went into how do we protect. How did the U.S. protect hardware that was going to live in the desert? And so certain technologies and certain things that were done there, a lot of that stuff doesn't necessarily translate well to the moon, because it's big and bulky, and some of the things we learned about soil stabilization and other things. A lot of it's really fascinating. And some of it, there's concepts there that's okay, this is really cool. How could this translate to the moon? Some of the things are even just things we would like to study. We try to sometimes just have interns or others just take this concept and study how could we take this thing that's used, say, in the desert, or use one of the things we did. One study we did is we took if people detail their cars, right, is the putties and the things that folks use to clay. There's clay bars and even putty that people use to clean their keyboard. Some of these we use to study how effective those are at dust mitigation. So, but it's interesting because even things that might be really effective at dust mitigation with space flight, there's other considerations, right? Like maybe these are really good at removing dust, but they off gas and they, like with some of the putties, for instance, they, what's the word? Disintegrate, right? Like over time. And so it's like, okay, it's like a mass trade, right? Like, okay, maybe you're sending this up, and if you could get past the off gassing and create like a material that didn't off gas or whatever, is it worth it? Because maybe it's really good the first time, but then the second time it's not as good. And then, by day 7, it's like, disintegrated and it's not even effective anymore, right? It's not even there anymore or whatever. So some of these trades are really fun to study. And so these are things that we've had like university students do and challenges, that we've had done just to kind of see like, could we do some of these things? So.
Yeah, there's a question from Rock right above Mike's question.
Oh, I don't see Brock's. I somehow missed that.
Arkit. So do we have any
Oh.
data from the Apollo missions if some of smaller particles of the lunar dust can get absorbed into the bloodstream? What effects that may have?
I don't know that one, but that would be a question for the toxicologists. So I can certainly, if you're really interested, I can certainly find out. So can ask the toxicologists. Someone else will know that for sure. So,
and most likely one of the goals or challenges that have in the human effects of the lunar dust or interaction with lunar dust. I'm not sure if
there's discussions about things getting into the bloodstream, like from cigarette smoking and diesel exhaust and all of these kinds of things, and what effects those particulates have, negatively on human health. So,
wow.
Yeah, it's like the plastics, right? The microplastics and the transmission of those compounds into all the parts of human bodies and all the organs of human bodies. And so that most likely if the inhaling of the lunar dust happens, then eventually it will get absorbed in one way or another, because it's not just inhaling, it's during inhaling people can swallow it as well, right? And process that and so on. And with the water, because there would be transmission and the contamination of the water with the dust somehow.
Sure.
I don't know, I'm just predicting it.
Yeah, no, that's interesting.
So it's and then just like right now they're finding microplastics everywhere in human bodies, we most likely will be in future finding the signs of lunar dust in different organs.
Got it.
Again,
okay.
Hypothesis.
Yeah, we just need
exposure.
Yeah, time of people going back and forth. Let's catch the next transport to the moon. Let's get the next transport back to Earth. And yeah.
And I did read. So one of the there's like a short version of like a very summarized version of the lab tag thing, and it said for particles less than 100 nanometers in size, sharp edges may aid their translocation from the alveolar region to the blood circulation.
So from the inside of the little sacs in the lungs, actually then going into the blood, just like oxygen, of course, has to do.
Right.
Yeah.
The near neutral pH value of the blood will make the dissolution of the dust particles more difficult. So anyway, another stuff that's over my head. So really good questions. Yeah.
But another stuff, most likely people need to be concerned, because again, that knowing what lunar dust is, the regolith with ragged edges, what impact, what effects to the bloodstream and blood vessels and the little very fine blood vessels that populates our organs with oxygen will also populate with those micro compounds, small, extremely small nanosize, right, of the lunar dust. And do we want that? Most likely not. But Yes, but the challenge will be is how can we eliminate? We can't scrub the environment into a, I mean, it's realistically most likely impossible, and especially if when we're concerned at that size of the particles, scrubbing, there's virtually no filtration system available that would be able to eliminate 100%. No one would, or
Right.
very difficult to expect that we can rate that, unless there's a certain discharge and so on that will be based not on the filtering using filters, but filtering with something else. And so that's a lot of research needs to be done in that area too.
Yep. And one thing that we talk about a lot is, well, I'm not gonna put the requirements there just because this is being recorded. But one of the things that we talk about a lot is some of the work that we're doing for lunar dust mitigation and how that might translate to Mars. So we actually have an intern, one of my interns who's been with me since May. We're like, let's change it up a little bit. And so in the springtime, he's going to be studying some of the challenges that we have with lunar dust mitigation and how those will feed forward into like Mars dust, right? Like the effects of dust on mechanisms, right? Maybe it's not as bad because particles aren't angular, right? But when you think about the human health effects, it's actually a totally different story there because and this is not my expertise because I'm not a geologist, right? But the perchlorates are actually like really, to my understanding, very bad, right? And so he's going to start talking to like geologists and other folks and like Mars scientists and start to get a good feel for some of these other challenges to say, okay, all the stuff that we are doing for like, say, understanding the human health effects of lunar dust mitigation, this is really important because while it's important for the moon, it's going to be critical for Mars because that could lead to even way worse things, right? That sort of thing. So, or different, right? Because if it's the angularity that's really bad from a lung perspective, for Mars, it's a different challenge. Maybe it's I'm not going to say it because my understanding could be wrong of the challenge there. But anyway.
So it's interesting about the perchlorates. Yeah, that's true on Mars. We have those. So Rock is also asking how similar are the properties, this is in the chat, of the lunar dust versus dust from the asteroids?
Yeah, that's great. That's a great question. I love that. So yeah, that was my background before. So asteroids are cool because they're so different. And so it really depends on the asteroids. And so, we're learning every asteroid we go to, and this is what they call it. Well, I guess fall's over, or just about over. Autumn asteroid. If you guys are paying attention at all, there's like all these missions, going to asteroids. Asteroid samples just got brought back. So we're learning so much. We know so much more than I guess I haven't really studied asteroids now in about 4 years, but asteroid regolith, that is. And so hold on, I'm trying to find the question so I can read it. How are the properties of lunar dust? So it's very similar in like the behavior, right? So like when we think about even like the way we engage is different from like a gravity perspective, right? Because unless we're talking about huge asteroids like Ceres, right? Generally speaking, the gravity on asteroids is very different. So when we're engaging with like back in the day, right, we talked about like the asteroid redirect mission, if folks remember that, and some other things, right? Like you can't really land on an asteroid. You have to like dock with an asteroid, for instance. And so the sample that we grabbed that we just brought back, like they had to like, it was like a grab and go kind of that's not what they called it, but I keep thinking grab and go tag, but they had to like kind of like grab it quickly, right? Whereas like on the moon, we have gravity, like you can land on the moon and like stay on the moon, right? And so some of the environmental conditions are different there, but like the no atmosphere, the way they were formed, there's a lot of similarities there. But the geological properties are different, right? Because the moon, and the moon's different, right? That's not geologically homogeneous. And I am, again, not a geologist, right? And there's differences in the geology of the moon, even in the mare and the highlands. So the dark part, when you look at the moon, the dark parts and the lighter parts, but asteroids are different, like body to body, right? Like there's totally different types of asteroids. And so the geology of the samples are totally different. And even the regolith, right? We assumed that all asteroids had regolith, right? And so then we went to one asteroid and there was like, well, where's the regolith? And I was like, as a person who studied asteroid regolith, I was like devastated, like, oh my gosh, this was not what we were expecting.
Right.
So there's so, to me, it's fun because there's so much we don't know about asteroids and about the surface of asteroids. So I personally think that what we're doing on lunar dust and dust mitigation and engaging with the surface and learning about the regolith feeds forward to asteroids and vice versa. I think the things that we're learning about asteroids and even like the samples that we grabbed, all of that stuff, I think it's all part of the same big story of how robots, how we engage with this kind of fine particulate. So
Very good.
yeah.
Okay, well, thank you so much. And
Yeah.
I just wanted to ask one more. Is there
Yeah.
one more question? Final warning.
Oh, mechanical properties. I see the question there. More from the perspective of mechanical properties. The particles on the asteroids are larger due to this. So yeah, there's a little, yeah. And now it's been a couple of years since I've thought about this and I should know this off the top of my head. But yes, there are differences there just in the formation. They are, because they're both airless, right, without atmospheres, you're going to have some similarities, but just the process that formed them is different. But you're right, the effects that we have now, they both have solar wind effects. They both have kind of this, we call like gardening effect and what's the word I'm looking for? Weathering, kind of generic term I think we use now is like weathering effects. And asteroids are a lot more dynamic, right? Like we look at some of the asteroids, like you'll look at pictures and they change, right? They kind of morph. And so over time, just because the gravity and the bodies, the way they're moving. So yeah, but that's not really the mechanical properties. So there's a lot. One of the things I did do when I first got to NASA as a postdoc was try to understand the mechanical properties of asteroid regolith, which is really hard to do because we were like totally guessing at that. And so there was like an Einstein quote that I really liked that was like, it wouldn't be called research if we didn't know what we were doing, right? Or something like that. So it was really hard to do. And so that's, again, where we're like learning by getting samples, bringing them back, or by sending, probes and learning. And so, sorry, I don't think that's a very good answer. But yeah, there are the geological effects that formed the moon are a little bit different, but then also the effects that are being imparted on them from the solar wind. I think that's similar. Yeah, so that's a really good question.
Well, it's great. Thank you for everyone asking questions, and especially Kristen for answering and presenting, introducing just really on a very high level of all the challenges and different system challenges that lunar dust presents for future exploration. And so with that, thank you, Kristen, for giving some ideas with whom to connect for additional presentations. So that's a great, thanks for introducing to Ron, for example.
Yeah.
And with this, again, appreciate you coming today on Saturday and talking with AWA Houston section. Mm-hmm. And looking forward to future cooperations.
Mm-hmm.
Awesome. Thank you. And I think I'm going to join this crew of Saturday Space Geeks. You guys are awesome.
Yeah.
Oh yeah,
we
absolutely.
cover lots of topics and yeah, it'd be wonderful to hear and see more from you. Yeah.
Awesome.
Okay,
Awesome.
I will stop recording for now. Mm-hmm. And